And the idea is that after this session, you will be able to build and train your own model in Google Cloud, and it will seem easy for you. So this session is going to be very practical, very hands-on, with lots of code snippets, as well as high-level diagrams and discussions. So what exactly does it mean to build and train a stock price forecasting model in the cloud? What does it entail? There are three components. First of all, market data is supposed to be in the cloud. What does it mean? It means that the data is hosted in the cloud and is available to you via native cloud APIs. Second, what does it mean to do data processing in the cloud? It means that you're using tools and services that are also native to the cloud, and all your data processing pipeline end-to-end is native to the cloud. And finally, what does it mean to train your model in the cloud? It means that you're using cloud services to train your model as a distributed application with multiple jobs running concurrently and training your model at much higher scale potentially and much faster. So market data is key to models. This is what powers financial models, and this is what brings them to life. And one of the key leading financial market data companies is Google Cloud's strategic partner, Thomson Reuters. And with this, I'm turning it over to Mike.
Thanks, Alex. What I'd like to do over the next several minutes is just give you a quick overview of the journey Thomson Reuters is taking in terms of bringing our data sets to the cloud, and specifically what we're doing with Google, and then give you a quick overview of the actual data asset Alex is going to be using for the stock forecasting model. Now, as Alex mentioned, market data certainly powers financial models when you want to run those. Thomson Reuters itself, our data and solutions power the financial services industry. Our data, for those of you who aren't aware of who Thomson Reuters is used by 10 of the top 10 global banks. 90% of all companies managing over $10 billion use our solutions, and 87% of the institutional investors, top global research firms, also use our data. Now let me give you some insight where and how our data is actually used. Now Thomson Reuters is an open platform that's cloud enabled. We call it, it's branded as the Electron Data Platform, and basically what it does is it serves the major functions of an institutional firm around the globe. Let me highlight a few of those. The divisions, the investment banking, sales and trading, wealth management division, commercial banking, retail banking, risk and regulatory, to name a few of them. Now, the Electron Data Platform itself is a set of services, analytics, integration tools, and then ultimately content. And content is really the foundation of the platform itself. If I take a look, I'm sure this is an eye chart for those of you at the back, but what it represents is one of the most extensive data set Thomson Reuters has in the industry. It spans all the way from the award-winning and leading Reuters News and Commentary, which is available not only as human-readable text, but also as machine-readable real-time feeds. Then it spans through market data pricing, security reference data, risk and regulatory, a very wide range of company data, and then wrapping up risk compliance and supply chain data. Now, it's one thing to have all the data, though. How do we make that available to our clients? As I mentioned previously, we have the Electron Data Platform, which, again, it's our journey that we're moving that towards the cloud. Now, most of the data within the financial service industry functions in a cycle. And let me use an example to explain what that cycle actually represents with real-time data. If we were to look at what we collect from exchanges, over 500 of them globally around the world, we take all the security activity from the exchange, we bring it in, normalize it, enhance it, and then tag it with common identifiers. From there, it's now ready for distribution to our clients, either through a suite of our own APIs, or as we progress, making it more and more available through the cloud itself. Let me give you some insight on the strategy Thomson Reuters is taking as we go to the cloud. There's three primary pillars to our strategy. For our own internal systems, it's cloud first. So everything we're doing, we're building in the cloud. Secondarily, where it's more important, how do we get our data out to our clients? We're evolving with the industry and providing that data through various methods, as I mentioned, native cloud services, we'll talk more about Google BigQuery later, or through our own suite of APIs available in the cloud already. The last area is transforming our own previously deployed systems and making those as a service in the cloud, where basically, again, we've pulled them out and have a zero footprint in our clients. Now let's look a little more specifically at that. From recent surveys from our clients, they've given this perspective on how they're moving their applications to the cloud. Down the right-hand side for financial institutions, it's basically the trade life cycle, all the way from pre-trade, trade, post-trade middle office activities, compliance, and then ultimately the back office technology wraps things up. Across the top, what we've got is we're charting between what clients have done today and what they expect to do in the future in terms of prioritization and moving to the cloud. And across the bottom, it matches nicely with the type of data, either relatively static historical data right now, all the way through to the future where real-time transactional services will be required. And what we've plotted out is what clients have told us they've been deploying to the cloud already. And there's a few general things that we can observe from this. One is the applications are across the entire trade lifecycle. So no one's shying away from deploying applications anywhere within their business. And then ultimately too, a lot of it's being used for analytics and reporting type capability. Out in the future, clients expect that there's some things that still need to be worked out to really get truly low latency data in the cloud, and it'll prove out over time if that's a valid use case or not, for example, for algo trading. Finally, to summarize things, a lot of the data right now is relatively high volume data and therefore is used very efficiently by cloud services. Which brings us to tick history data. One of the largest data sets within the financial services industry is tick data. Tick data, for those of you not familiar, is really the collection and storage of all trade activity, bid and ask prices and everything for security in the market. So we collect that up, and as mentioned before, that's part of what we process through our EDP platform. Now, back in 1918, you see how they worked aboard to store that information. Certainly there's been a lot of evolution in that data since then. I don't think these two working the board could keep up with today's volumes or necessarily worried about nanosecond timestamps. Specifically now, what clients can do today in accessing Thomson Reuters tick history data in the cloud is they can take it through our web services APIs, or as a proof of concept right now, as we sort out the most efficient methods, we've actually loaded a few years of 20 years history of the New York Stock Exchange data right into the BigQuery tables. It's very efficient for using training models and doing simulations on that volume of data. It's one of the ways you can access over the 20 years of history of market-leading quality of the 400 exchanges we've collected it from. And then ultimately too, when I talked about enriching data, here's a perfect example. We've taken all the corporate actions, whether it be splits or dividends, and that's already incorporated for you. And then ultimately too, if you're linking it with other data, it comes in the same format with the same set of identifiers you've already used. A few other benefits you don't have to worry about by managing in the cloud. You don't have to worry about collecting the data and managing that infrastructure. You're not going to worry about the database CPUs and servers and managing them. And then ultimately, for disaster recovery and backups, also part of the built-in services of the cloud. Now, to go specifically, what did we actually put in? So I said as a proof of concept at this point, we've worked with a number of clients. We've taken 3 years or so of the New York Stock Exchange data. We've put it in a table. It represents the trade and quote data that goes on. So for example, we've got an identifier, which is the RIC or the Reuters instrument code. We have a number of other fields in terms of the time, the bid, the price. Ultimately, the trade data includes similar information. If we want to get access to it, it's as simple as a SQL query. We just list the fields, the date, the fields of the table we want to pull it from. In this case, we're pulling gs.in, which is Goldman Sachs from the NYSE. And then we say we want the quote data. Voila, this is what we're going to get back very quickly. If we want to do similar for trade data, just a slightly different query, we're going to modify the fields, say that we want to pull trade data, and here's what we've got. This is the data that Alex is going to be using to explain the model. So I'm going to pass it back to him now so he can explain how he's leveraged Thomson Reuters data along with the Google Cloud capacity so that you can make it easier for yourself.
Thank you, Mike. It was great. Okay, data processing pipeline. Now the fun begins. We're going to take a look at how to put together the data processing pipeline, and before we get into nitty-gritty details, I'll give you a high-level overview of what we're going to be doing. So the first step is we're going to generate model features starting from the Thomson Reuters data in BigQuery, and this can be done from a Python script or from a Colab. In case you don't know, Colab is an extremely useful tool built by Google. It's a hosted Python notebook. It's hosted in Google Cloud. It's a free service. When you use it, you get access to cloud services, and you even get a free GPU on the cloud. You don't have to pay for it. And in Colab notebooks, you can write your code, you can execute your code, and you can see the output all within one notebook. And it's very convenient for sharing with your teammates, for example. Okay, second step in the data pipeline is we're going to write model input features into what is called CF record files. So this is the standard format for representing input features data for TensorFlow models. The third step is we're going to launch model training using Cloud ML Engine. When the training job starts, the workers will be loading model features from TensorFlow record files that have been previously written to Google Cloud Storage. And periodically, the worker jobs will be saving model state checkpoints as well as training and evaluation statistics in a bucket in cloud storage. So that's the pipeline. Now let's take a look at model predictions. What we're going to be predicting. Let's start with that. What metric will the model be forecasting? When we're talking about the stock price forecasting model, the key is to define what horizon we're talking about. Are we going to be forecasting for a year, for several months, days? So to be specific, for this example that we're going to show you, we're going to be forecasting intraday stock returns with 5-minute horizon. The reason we chose this for this example is because this is something useful, practical. It's useful for scheduling orders, for algorithmic execution algos, and it's useful for intraday trading strategies, so it's something relevant. Now let's take a big picture view for a moment and discuss a little bit what exactly we're going to be doing here. We're going to be using supervised learning, meaning that we're going to be training our model on examples. Each training example is a pair comprising input features and the correct answer. So input features are whatever inputs the model is going to be using to give us their prediction. And the label is the correct answer. So given inputs and correct answers, the model will be learning and learning until it hopefully is able to generate correct or more or less correct predictions even when it doesn't know what they're going to be based on the inputs. Okay, so what are going to be our labels? How do we construct the labels, predictions? So our goal is to predict intraday returns for a 5-minute horizon. And for this, we need to define the starting price and the final price, the end price. For the starting price, we're going to be using the average PLAS midpoint for the current 10-second interval. And for the final price, we're going to be using 5-minute volume-weighted average price, or VWAP, for the 5-minute interval subsequent to the current point in time. And that is actually relevant because when you schedule sub-orders, you want to know what will be the VWAP, not just some price at some random point in time, but VWAP may be more relevant here. So this is the picture that illustrates what exactly we're doing. We are calculating the average midpoint. We're calculating the VWAP for the next 5-minute interval, and we take the logarithm of those two values, and the difference of logarithms is the label that we're going to be using for training the model. So after we're done with building and training the model, we're going to be taking a look at evaluation statistics to see how well the model performs. But I guess you're already curious to see how it performs, and so we're going to have dessert first before we're done with the main entry. Okay, so this is what we did. For this example, we trained the model on 16 days of Thomson Reuters market data between May 1st and 24th. And we evaluated the model on one day of market data, May 25th. So you can see that the evaluation data should always be after the end of the training data. You don't want to have any look-aheads here. And we're using R-square as a measure of the quality of the model. What is R-square? Approximately, it tells you how good is the model compared to a trivial model that always predicts 0 return. So for this particular example, R-square was 0.1, which means that the model was useful. If R squared is 0, it means the model is as good or as bad as the trivial model that always predicts 0 returns. If R squared is 1, it means the model is perfect. If it's between 0 and 1, it means it has some predictive probability. So here you can see that for the 0 prediction model, the mean squared error on evaluation data was 231 squared basis points, where basis point is 101%. And the mean squared error for the for our model on evaluation data was 207, so it was slightly better than the trivial model. And this is roughly what would be expected, because you do not realistically expect to forecast all or even most of the variance at 5-minute interval, because there is a lot of noise in intraday prices. Okay, so let's take a look at how we build the inputs. What are we going to be feeding into the model? We're going to be defining input features based on what types of factors that affect stock returns we're trying to capture here. Okay? So first, we're going to learn intraday price patterns at different times of the day. And to do this, we're going to include a feature based on the intraday sequence number of the current 10-second interval. Then we want to capture mean reversion or momentum price patterns, and for this we're going to be using a list of differences of logarithms of average midpoint quotes in the last 120 10-second intervals. So essentially what this means, this long sentence, is that we're looking at returns between consecutive 10-second intervals for the trailing 20-minute window. And we're using this list as one of the input features. Then we want to capture price patterns for stocks at different price levels, and for this we're looking at the logarithm of the price at the current 10-second interval. Then volume is also relevant, and so as one of the input features we're going to be using volume in the trailing 20-minute window preceding the current interval. But for this to be useful, we want to normalize the volume by the stock's average daily volume over some reasonably long time range, and for this example we use 4-week average daily volume as a normalization factor. So we take trade volume for the stock in the last 20 minutes, and we divide it by this stock's average daily volume over the past 4 weeks. Okay, and finally we're going to be using an input feature based on the stock's security identifier, RIC, because different stocks may have their unique, distinct intraday price patterns. And I will show you how to plug in a RIC or string in general into the model. Okay, now get ready for some heavy construction work ahead. I'm going to start showing you some slides with the actual SQL code snippets. So first of all, we're going to be using BigQuery. What is BigQuery? It's Google Cloud's enterprise data warehouse, ideal for analytics. You can run standard SQL queries on it, and also it has some very useful extensions, analytic functions. I will show you how to use those functions. It's fully managed and serverless, meaning that Google takes care of provisioning of CPU and storage capacity, of data replication. You don't have to worry about any of that. Okay, feature number 1, intraday sequence number of the current 10-second interval. So what I want to do here is basically calculate the number of seconds since midnight and divide by 10. And to do this, we extract the hour, multiply by 360. We convert from UTC time into local time because we care about stock patterns specific to the exchange's local time, not UTC time. We extract number of minutes, multiply by 6, and we extract number of seconds, divide by 10, and round it up. So this is our interval sequence number. Okay, building block for feature number 2, list of 10-second interval midpoints. One nice thing BigQuery provides is the ability to use temporary tables as a part of your query. So you can, in this example, we use interval midpoints as a temporary table. You write a query, and the output of the query is stored in the temporary table. And then we can use this table from within another query. And here we're using array aggregation function, which is an analytic function of BigQuery that allows you to apply certain function over a series of rows preceding each row in the output. So what I want to do here is to partition data by RIC, and the overflow specifies how exactly we're going to do it. So partition data by RIC, by stock identifier. Within each partition, we order rows by interval sequence number. And with this ordering for each row, we take 120 preceding rows and make a list of them and return this as the output of the query. Okay, feature number 3, normalized traded volume. So there are 3 steps here, as I mentioned before. We compute each stock's average daily volume for the last 4 weeks. We compute interval volumes, normalize them by AGV, and then for each interval we compute the sum of normalized volumes for those 10-second intervals in the preceding 20-minute window. So there are 3 steps here. And similarly as before, we use a temporary table to store average daily volumes. Then we use this temporary table from another query to calculate interval volumes normalized by AGV. And then we use those values from yet another query in which we use an analytic function called sum, which instead of making a list of rows, values from preceding rows, here it just adds up values from a list of preceding rows. And just before we specify that we want to specify that we want to partition data by RIC, we want to order rows in each partition by interval sequence number, and for each row we want to apply the sum for 120 preceding rows. Okay, now I'm going to show how to construct building block for the label, VWAP, in the 5-minute period subsequent to each interval. This is something that we won't have when we're generating forecasts, but this is something that we're going to have when training the model. So once again, we use a temporary table for interval price volumes. We use this table from another query, which for each row, for each interval, computes the sum of price volumes and divides by the sum of volumes. Okay, now one thing that's very convenient about using BigQuery for data in Google Cloud is that it's very nicely integrated with Python. There is a pandas package called IOGBQ that has this method called readGBQ. You can pass the query, you pass your project ID in Google Cloud, and it returns the output of a query into a pandas data frame. And then you can do additional transformations of data, generation of final features from our semi-final results of queries directly within pandas data frames, which have very rich functionality. So it's very convenient. Now, once you have this final data frame with all features that you need, you can save it into a JSON file with the toJSON function. JSON format is very convenient in that it preserves the structure of data. So for example, it will save lists as lists. If you use toCVS function, for example, it will save lists as strings and you lose the structure. So I recommend toJSON. Then finally, if you wish, you can use JSUtil tool. It's one of the tools in Google Cloud to copy your JSON file into one of the buckets in the cloud. Okay, generating TF record files. So TF record is the recommended format for storing serialized model features in TensorFlow. So what we do, we run queries in BigQuery to get the data, we put data into data frames, we apply additional transformations, and then we use those data frames with everything prepared to generate TF record files. And those files will be later fed to the model for training. So there are 3 steps here. Generating training examples comprising model input features, serializing training examples into TF record files, and feeding TF record files into the model. So what is a training example? It's actually a Python dictionary or map. It maps feature names to feature products or protocol messages. And there are 3 types. You can have a list of bytes, a list of floats, or a list of integers. You always have a list. And what do you do with features that are scalars? If it's on a list, you simply have a list with one element in it. So there is an example. There is how you construct an example, assuming that each row holds values of features from our data frame that we have constructed earlier. So delta log sleeve this is what we're going to be using for our label. This is the correct answer that we only have during training. We don't have it when we're actually using the model to make predictions. And we have 5 features that I described earlier: the rig, stock identifier, interval sequence number, deltas of log meets, sum of interval volumes, and logarithm of the current mean. Okay, how do you use this to actually generate TF record files? The first step is to initialize the TF record writer. Then you iterate over rows in the data frame that contains your features. And for each row, you construct an example based on that feature dictionary that I showed you on the previous slide. Then you serialize this example and you write it into the TF record writer. Finally, when you are done, you are closing the writer, and you have this file with serialized TF records. If you only intend to train your model locally, you can generate this file in a local directory. But if you are planning to use CloudML Engine, you have to copy this TF records file into cloud storage so that it can be accessed by multiple jobs, multiple tasks that are running as part of the CloudML Engine job. Okay, preparing data to train the model. So TF records can be efficiently fed into the TensorFlow model for training and evaluation. And in the next several slides, we're going to look at exactly how we're going to be feeding those models to our model. And there are 3 steps here. The first step is we're going to define feature columns, and I will show it to you in a moment what they are. Second step, we're going to create a parsing spec. And third step, we're going to define an input function that will use the parsing spec. Okay, step 1, defining feature columns for the model. So feature columns is a list. It specifies the type of each feature. So here, for example, for the rig, we're using what's called an embedding column. We're plugging stocks identifier, a string, as an embedding, which means essentially that we're mapping the string into a numeric value. And this numeric value may represent, for example, stock's propensity to have mean reverting versus momentum price patterns. And one caveat that you need to be aware of is when you use embeddings, you want to make sure that you set hash bucket size to large enough value, because you certainly want to avoid collisions in the hash map used for embeddings as much as possible. So essentially, when you have collisions, the model doesn't distinguish between 2 different rigs in this case, and you don't want to do that. Then you have feature columns for other model inputs, in this case interval sequence number, sum of interval volumes for the trailing window, and logarithm of the current mean. You can see that we specify their shape. The first dimension is 1 in all cases, meaning that they all have width 1. They're all scalars. And then we have delta log meets, for which we specify shape with the first dimension set of 120, reflecting the fact that it's expected to be a list of 120 values. Okay, step 2 here is creating parsing spec, and this is very easy to do with a function called makeParseExample_spec. So you pass this list of feature specifications to this function, and it gives you feature spec that we can use in the input function, which is the next step. We're going to define the input function in the next couple of slides. Let's see what we're doing here. The first step is constructing a data set. And for this, I recommend using a function called makeBatchFeaturesDataSet. It creates already performance optimized data set with batching and shuffling built in. So you don't need to worry about reading your data efficiently. You don't need to worry about setting up multiple threads to read your data, because sometimes it's a bottleneck. It does everything for you. So where previously you would make several function calls, here you can just use this function. So let's look at the parameters here. The file pattern specifies the list of files of TF record files that you have generated previously. So for example, you can have a separate TF record files for market data from distinct trading days. Then batch size, so here we set it to 128. What this means? It means that the training examples are going to be passed to the model not one by one, but all together in batches. And each batch is going to have 128 training examples. When you feed training examples to the model, it generates predictions, and the loss is computed for the difference between predictions and actual correct answers. And then based on the loss, the backpropagation of gradients is applied. So when you use a batch, the backpropagation happens only once for the entire batch. All gradients are averaged over all training examples, so then there is backpropagation happening once. So this is called mini batching. And usually it improves model performance when you train it with batch size at around 100 to 1,000. Now, the feature spec is what we constructed earlier. Number of epochs is set to 1. This simply means that we're reading the data set just once. You can read it several times if you wish. Shuffle is set to true. What this does, it randomizes the order in which it puts training examples that it reads from the file into batches. It makes model more robust. Then we make an iterator. So make one shot iterator, it simply creates an iterator that reads the data from the data set just once. There are other types of iterators, some of them read data more than once. And this is interesting, the getNext function. So it looks like, if you look at this function, it returns features, but in fact it does not. What this function returns is an operation node in the computation graph. And then later on, when this node is evaluated, it will return next batch of examples every time it's evaluated. And this is a very important subtle point, so I have a separate slide just for this, because it's a key point to understand. TensorFlow programs in batch mode run in two phases, in graph mode, sorry. In graph mode, they have two phases. In phase 1, you construct a computation graph, but no data is flowing through the graph yet. Then in phase 2, you execute the computation within the TensorFlow session. And this is when data actually flows through the graph. So in our function, data set input function, as it's implemented, it doesn't return any batches of data yet, but instead what it does is it adds nodes to the TensorFlow computation graph. And then when later on the nodes are evaluated within a session, they will be returning next batch of training examples upon each evaluation. So you see this, so we're back to data set input functions. It returns features and labels. So features is an operation node in a TensorFlow graph, and labels is another operation node in TensorFlow graph. Okay, training the model. First we're going to look at how to train the model locally. So the model will be training on examples we feed it, and with some number of examples on which it trains, hopefully it will learn how to make correct predictions. That's how supervised learning works. So the first step is to construct a DNN regressor. TensorFlow has several built-in estimators. So DNN regressor is one of the estimators, and it's intended for use with models that make numerical predictions, which is what we're doing in our example. Hidden unit specifies the structure of the neural network. So here we are going to be using two fully connected layers, and each layer is going to have 128 hidden weights. Feature columns, so this is exactly the feature columns that we defined earlier. It's a list of specifications of the dimensionality and type of each input feature. And model directory is an important argument that specifies where the model is going to be saving its periodic checkpoint, so its state, and where it's also going to periodically saving its training and evaluation statistics. Okay, so here I'm again going over the feature columns. There is a embedding column for the rig, there is numeric column for interval sequence number of shape 1, sum interval column shape 1, log current meet, they all have width 1, and delta log means has width 120. Okay, and I already said that model directory is where the model stores its checkpoints, and this is also importantly the directory from which the model reads its state to initialize when you construct an regressor later on. And by using this feature, you can train the model iteratively or incrementally. So the way it works is you initialize an regressor from the latest checkpoint, then you train model on newly available data, for example, on newly available data set, and your checkpoints will be automatically saved in the model directory. So it will create new checkpoints with files under new file names, and will automatically garbage collect old checkpoints. So, for example, in case of financial data, you can incrementally train the model at the end of each trading day. So, at the end of the trading date, you collect all market data for this date. You train the model on training examples for that date. The model starts with a checkpoint from the previous date. After it trains, it saves its state in a checkpoint, representing its state after it has incrementally trained on market data from today. And then tomorrow it can go on. Okay, so how to train the model? One thing before we get to training is you may want to add some custom performance metrics, evaluation metrics. By default, the regressor has one metric. It shows L2 loss values, which is mean square error. And it may be useful to have root mean square error as well. So this is how you add the custom evaluation metrics. And okay, so we're almost at the point where we're training the models. Before we train the model, we need to construct training spec and evaluation spec. And what this does is primarily you specify input functions. So we can use the same input function, but simply initialize them differently with different lists of files. We pass a list of training files into the train specification, and we pass a list of evaluation files for the eval specification. And very importantly, when training models, evaluation data should start after the end of the training data. You don't want to have any look-aheads here. And also it's important to specify the number of maximum steps for training, because depending on how you implement your dataset input function, if you don't specify this, your model may train forever, it will never stop. Okay, and finally, train and evaluate functions, the recommended way of training TensorFlow model that uses DNN regressor. What it does, it trains the model, it theoretically checkpoints the state, and it theoretically checkpoints training and evaluation performance metrics, all in the same directory, but there is a separate subdirectory for evaluation metrics. Okay, now we look at how to train the model locally. Now let's take a look at how you will do it with the CloudML engine. So why would you want to use CloudML engine? The primary purpose is it gives you scalability. It gives you the ability to train the model with multiple workers, multiple tasks at the same time. This way, you can train your model many times faster, and you can have much faster turnover over different versions of the models you want to try. You can do your research much faster this way. So the good thing is when you transition your model from local training to training with CloudML engine, you don't need to change your code at all. When you're using estimators, they already have built-in support for CloudML engine, and that's extremely convenient. So all you have to do is to specify configuration file, you need to specify code to construct training package, the setup, and you need to provide the main program to train the model, which you already have, because it's the same program. So configuration settings, you need to specify the scale tier. In this example, we're going to be using a custom tier because it's the most interesting, most flexible. You can specify exactly the hardware configuration for different types of nodes in your training job. So let's take a look at the different types of nodes. There are three types. There are worker nodes, which calculate gradients. There are parameter and workers are the nodes that do lots of numerical computations, matrix multiplications, and they are the nodes that you will want to run with GPUs to get faster performance. Then there are parameter server nodes which update parameters with gradient vectors from workers, and then there is a master node which coordinates everyone and also operates as a worker. So based on that usage, we're going to be using standard GPU for master and worker nodes, and we're going to be using standard CPU for parameter servers. And we also get to specify how many workers and how many parameter servers we want to use. For this example, we're going to be training a model with 8 workers and 4 parameter servers. Okay, the code to construct training package, there is a separate file you need to provide, and you specify the list of required packages. In many cases, this list will be actually empty because each CloudML engine runtime comes with already built-in list of many popular Python packages. So if you are using something that's very non-standard, you may need to specify it here in this file in setup, but in many cases you won't need to. And the main program to train the model is the same as for local training. And again, let's go over what it does. It parses command line parameters, it defines feature columns, it constructs CNN regressor, defines evaluation metrics if you need any. It defines the input function that will be reading TF records from a list of files, and it will start training and evaluating the model. So this is the command used to submit a job to CloudML engine. You need to specify a unique job name. You specify the path to your main program that does the training. This is the program that creates CNN regressor and calls train and evaluate function. You specify the path to your configuration file. You specify the path of your staging bucket in cloud storage. And you specify the runtime version. So this number, the runtime version is exactly the version of TensorFlow. So depending on what version of TensorFlow you intend to use, depending on your code dependencies, you will specify the version here. And as I said, each runtime version of CloudML engine comes with a different list of packages already built in the runtime. Then we need to specify the region. There are 2 regions supported at the moment, US Center 1 and US East 1. And finally, if you need to, you can specify a list of custom parameters that will be passed to your training application. Okay, evaluation of the model. So what is evaluation? The key question we want to answer is how precise is our model? What's the quality of predictions? How well does it perform on evaluation data? So we're going to be using TensorBoard for this. This is how we run a TensorBoard, and you command is called TensorBoard, and then you specify the directory where model checkpoints are, and evaluation statistics and training statistics are saved. This is the same model directory that we used when we constructed the CNN regressor object. Okay, so this is what L2 laws look like on the training data that we use for this model example. This is what the loss looked like for the first 3.5 hours of training. You can see that it started, L2 loss started around 90 probably, and it was gradually decreasing over the next 2.5 hours, meaning that the model, as the model trains, its loss on training data becomes gradually lower and lower. But this doesn't necessarily mean that the model is becoming better in its predictions, because what we really care about is the quality of generalizations. And when we look at the L2 loss for evaluation data, we see that the model starts around 206 after 30 minutes of training. And then actually, you can see that loss on evaluation data increases slightly to around 210, 211. So what this means is you probably may want to stop training your model after first half an hour, because after that, L2 loss on training data will keep decreasing, but this simply means that the model gradually starts overfitting. So you want to stop training because you're not going to improve quality of predictions after that. The longer you train after first half an hour, in this example, the worse actually the model will predict on evaluation data. So there is usually an optimal amount of training you want to apply. Okay, so I said this already. And let's take a look at the R-squared. So as I mentioned before, R-squared gives you an idea of how well the model performs on evaluation data compared to a trivial model that always predicts zero returns. And as I said, if the value is 0, it means the model is worthless. If it's 1, it means the model is perfect. And usually we expect the value to be closer to 0 than to 1, but to be positive. And as it happens, that's the case here. R-squared is approximately 0.10 to 0.11 after first 20 to 30 minutes of training. And then it declines to a range between 0.08 and 0.09, which is actually decent for when you're predicting 5-minute prices, intraday prices. But remember, this was based on model trained on only 16 days of market data and evaluated on only 1 day of data. So this is fine for an example of how to build a model, how to train it, but this is not what you would want to do for actual use in production. For use in production trading, you would want to train your model several years of data and evaluate on several years of data. Okay, generating forecasts. Once we have the model, how do we generate forecasts? For training, it's convenient to save data into record files. When you want to build forecasts in real time, it may actually be more convenient to store data in data frames, in pandas data frames in memory than to read from files. I will show how to do it a bit later. So the key is that for generating predictions, you use the same initialization settings as when you were training the model. Same hidden units, same model directory, same feature column, so that's important. As I said, we're going to be using pandas data frame. And when input functions based on a pandas data frame, each data frame row is going to include feature values for one training example, and each column is going to have feature values for one feature type. And the input function is going to return a dictionary mapping names of input features to tensors containing the features values for the entire batch. So essentially values for one column in the pandas data frame. So the feature tensor will be two-dimensional. The first dimension is the size of the batch, which is the number of rows in data frame. And second dimension is the width of the corresponding feature column. So we have RIC, we have interval sequence number, sum of interval volumes, log of the current mean, delta log mean. So you see here the second dimension is 120. And there is a little bit different transformation here because first we need to convert the list of lists into NumPy multi-dimensional array, and then we shape the array as required with the second dimension set of 120. Then we use the predict method that returns predictions generator. We use islice method to get the iterator. And here it's important to specify the number of steps in the iterator, otherwise it may never stop. And then as we iterate, we get this list of predictions which correspond to rows in the data frame. So the length of this list will be exactly the length of the data frame, the number of rows. So the wrap up, what have we accomplished? We have shown how to build model features using Thomson Reuters data in Google Cloud using BigQuery. We have looked at how to serialize input features into TF record files in cloud storage. We have seen how to construct linear regressors and build and train the models locally. And we have seen how to train the model as a scalable distributed application using Cloud ML Engine with multiple workers. And now we hope that we invite you to apply the knowledge that you have gained in this session to try and build and train your own machine learning model in Google Cloud and put all pieces of your own puzzles together into a beautiful picture. Thank you.